So we, instead of computing the exact forms, analysis forms of the integral, we approximate it by some numbers. So that can apply for only for definite integrals, right? And we study left endpoint, right endpoint, trapezoidal rules to approximate an integral. And we study up to the point error estimation here. The error is the numbers that we add up to our computation to make an exact solution. For example, here, the trapezoidal rule, the error of that is this number, right? Subtract this exact numbers, which give us the negative 0.02, something's here. And the midpoint rules give us a different errors. So we see that this error here, trapezoidal rule, give us a negative number. It means our numerical result is higher than the real value of that, right? On the other hand, if the is below, On the other hand, if the error is bigger, is a positive number, it means that our result is bigger than the true numbers. So, and here are the two tables of the approximations with different method. The left end result, the right end approximation here, the trapezoidal rules, and the midpoint rules. We increase the numbers of points, the rectangles, right? The arrows is becoming smaller and smaller. So we see that if we do so study this, we see that the midpoint rules give us the smallest error compared to the others, right? But sometimes it's inconvenient because we need to discretize the domain and we need to evaluate the value of the midpoint. So the trapezoidal rules give us a small enough error, close, but it's a lot more convenient. It depends on the purpose you want to do. And here we can estimate the error. And it is proof that the trapezoidal rule is smaller than this number, where k is the upper bound of the second derivative of that function. Upper bound, it means that the second derivative is always smaller than that number. So we have it here. The b minus a here is the difference between the limits, right? And n here is the numbers of the rectangles, the intervals that we discretize. And the midpoint rules, the error of that, follow this inequality here. Okay, let us study this example. I think we can do quickly here. So if the function f of x is 1 over x here, we can compute the first derivative, right? Apply quotient rule. And then we do the second derivative, which is the derivative of the first derivative here, give us 2 over x cubed. Look at this. And the integral we study, suppose x is between 1 and 2. Okay. And the second derivative here is 2 over x cubed. In order to do error estimation, we need to know this number k here, right? Now, look at this. If this guy, it means x is larger than 1 and smaller than 2. From the first inequality here, if we flip, right, flip all these, the inequality will also be, we have to change the signs of inequality here, right? Okay. Are you comfortable with that? Or just do some algebra separately? You see it. And here, what do we have? It means that we have this inequalities, right? This number is smaller than 1. Okay, now if we raise to the power of 3, what do we have? A number smaller than 1. If we raise it to the power of 3, is it getting bigger or smaller? Yeah, smaller, right? So, but it's still, but it is a positive numbers, right? But it's still true here. Okay. Then we know that this is the second derivative, right? We want to somehow have the same terms here. And we can write this guy is 1 cube over x cube, right? And 1 cube is still 1, right? So in short, let us write it this way. The second derivative has a number 2 here. How can we make it happen here? Yeah, we multiply everything by 2. The inequality is still true, still holds. Therefore, we have that 2 is larger than this over x cubed 2 times 1/8 here, right? Or we have this inequality. Okay, simplify it. So this is how we get that. And we know that what we care is the upper bound of this second derivative, right? So it means that the number k we are looking for is this guy. So for any x between 1 and 2, we always, so are you okay with that now? Up to this point? Then let us go back to the slides. So the slides here, we always have that this second derivative is smaller than 2, right? Then applying to this error estimation theorems here, we know that the error for trapezoidal rules is always smaller than k, which is this number, right? Times b, which is 2, subtract 1, and raised to the power of 3, divided by the number of points. In this case, if n is 5, then the error here will be like this, okay? You can do the similar things to find the error of the midpoint rules, okay? So it's in the slides, so we can move on, okay? Go back home and study it yourself and make sure that you understand it. And here is another rule to approximate integrations. It's called Simpson rule. Suppose H is delta x, which is b minus a over n, where n is the numbers of the rectangles or the intervals. Then we can prove that for any, so if p here, suppose we compute the error, the areas of the quadratic curve which approximate these points, P0, P1, and P2, in the intervals from -h to h. Okay? This parabola, this quadratic, this curve fit this point. So these are givens. Suppose A, B, and C are the coefficient of this quadratic function, and we don't know what it is, okay? But we know that. So from this, we can compute the area of this domain. And it becomes a simple integration. And finally, we can find that error, the areas, depending on A and C. Okay. So, the point P0, P1, and P2 satisfying the curve, the given curve. Therefore, we have this relation. We solve this system of equation here. y0, y1, and y2 are the points here, right, which are given. From this, we can solve for A, B, and C, okay? And we find that the area under the parabola here is given by this formula. It is very nice because now it depends on the value here, right? The y0, y1, and y2 values. And h is given. So anyways, we can always find this area depending on 3 points here. It's beautiful. And now it is always true for this. If we shift this domain to the right side of x, right, it will stay the same numbers, right? It means that we can use this formula to compute the area from x0 to x2 here, following this formula. Okay. The same story, we can find the area of this guy using the same formulas here, which is h over 3, but now y0, which is this point, and y1 will be the second point, and y2 will be the third point here, right? Just apply formulas. So anyways, we can expand, we can write it in details, and the integral from a to b of fx dx here can be approximated by the sums of these areas. Okay. okay, which is the sum of h over 3 of y0, 4 times y1 plus y2. Then we move on to the next terms. Y2, it starts from y2 here, right? To y3 and y4. And the coefficient of them will be 1, 4, 1. Just memorize them. You don't have to prove it. Okay? And next, so on and so forth. This is the Simpson rule to approximate an integral. Okay? It's very nice. And it is named after this great mathematician. And the patterns of the coefficients you can memorize is 1, 4. Here you look at this guy. 1, 4, 1, right? Is y0, y1, y2. And then from y2, 1, y2, 4, y3, and 1, y4. So this combination gives us the number 2, right? 2 times y2 here. That is why it's appear here. So now, if we factor h over 3 out, the coefficient will be 1, 4, 2, and 4, 2, 4, 2, so on and so forth. At the end, it should be 4, 2, 4, 1 here, like this. 2, yn minus 2, 4, yn minus 1, and yn. Okay? This is the Simpson rule. And we can use this rule to approximate integral from 1 over 2, from 1 to 2 of 1 over h here. If n is equal to 10, okay? And we do the same things as we've done before. Just write clearly what they are, sum them up. You see that the Simpson rule, if n is equal to 4, now go home and try to do it yourself here. When n is equal to 4, double check if the midpoint rule here and the Simpson rules here, if you got the same result. Okay? So that is all about the error, the approximation of integral. And the error of these two methods, we see that the Simpson rule here gives us a better result with the same numbers of intervals, the rectangles, right? At n is equal to 4, the error of the midpoint rule is good already, but the Simpson rule gives us a better error, smaller, right? It is also very nice that we can estimate the error of the Simpson rules, and it follows this inequality. The same story. We need, in this case, we need to compute the derivative, the fourth order's derivative of this function. So that's all about the approximation of integrals, Simpson rules, midpoint rules, left n triangles, right n triangles, etc. So